All right, today we're going to start with section 1.1 in our text. And section 1.1 is about inductive and deductive reasoning. So we'll look at those two different types of reasoning today. Now, just so you know, at the top of the text, I do have a citation. So all the definitions and pretty much most of the examples are going to come from your text. So if you want to look back in your text for further detail, or sometimes additional citations and things like that, please definitely go ahead and do that. I also try to pull out the key information, so I do suggest you still go back and read through your text each and make sure you look at all the examples there, as we don't always cover every single example in our lectures. Let's start by introducing some of those key words and definitions, and we're going to start in this video by looking at inductive reasoning. So mathematics first is a science that helps us to recognize, classify, and explore the hidden patterns in our universe. So really everything we do is really about patterns and like the procedures that we see occurring over and over again. In everyday life, we frequently rely on patterns and routines to draw conclusions. Inductive reasoning. For instance, if we found out the last 6 times we went to the beach, the traffic was light on Wednesdays and heavy on Sundays, we may conclude that traffic is lighter on weekdays when heading to the beach. This type of reasoning is called inductive reasoning. So we take a look at what's going on around us. We look at the patterns we see. So we take those specific examples, and then we make an educated guess to say, okay, well, what is likely happening or what's going to happen next? So if I know that I've gone to the beach 6 times, and every time the traffic was light on a weekday and heavy on a weekend, then I'm going to start to conclude or make that educated guess that the next time I go to the beach, if I go on a weekday, I'm going to hit less traffic. So that process is inductive reasoning. It's a process of arriving at a general conclusion based on observations of specific examples. So with inductive reasoning, what's happening is we're going from specific examples to a general conclusion. All right, so we're taking our specific examples of what we're seeing happen and we're making an overall statement of what we think happens in general. Although inductive reasoning is a powerful tool, we can never be absolutely certain that these conclusions are true. For this reason, the conclusions are called conjectures, hypotheses, or even educated guesses. A strong inductive argument does not guarantee truth of a conclusion, but rather provides strong support for conclusion. If there is just one case for which the conjecture does not hold, then the conjecture is false. And such a case is called a counterexample. So here's an example. The 10 symbols that we use to write numbers, namely 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, are called digits. In each example shown below, the sum of two two-digit numbers is a 3-digit number. For instance, 47 plus 73. So those are both 2 digits. And when I add them together, I get 120. So I have a 2-digit plus a 2-digit equals a 3-digit. And then I have another example, right? So if I did 56 plus 46, and I go ahead and I add those together, I see that a 2-digit plus a 2-digit equals a 3-digit. So I may conjecture that every time I add two two-digit numbers together, I get a 3-digit number. Well, is that true? So is the sum of two-digit numbers always a 3-digit number? Well, the answer to that is it's false. It's not true. And I can prove that by finding a counterexample. So this is a great time if you want to pause the video, see if you can find a counterexample of your own to see if you can find one that works. So one example is the number 12 plus 13. Right, so those are two-digit numbers, and I'm going to add them together. 3 and 2 is 5, 1 and 1 is 2, and what happened was my answer was not a 3-digit number, but a 2-digit number. So this is false. We don't always get 3-digit solutions. Sometimes we can get a 2-digit solution, right? So this is a false statement here. So we have a counterexample that proves something is false. So when we're making conjectures, when we're making hypotheses or educated guesses like this, we actually can never prove it's true just based off of our conjecture. But we can prove things are false by using these counter examples. So let's look at examples of strong inductive arguments and then a weak inductive argument. So here's an example of a strong inductive argument. So although we can't 100% prove it just based off of induction or inductive reasoning, we can feel pretty confident in our educated guess, right? So it's a strong argument. In a random sample of 380,000 freshmen at 722 four-year colleges, 25% said they frequently came to class without completing reading or assignments. We can conclude there is a 95% probability that between 24.84% and 25.15% of all college freshmen frequently come to class unprepared. Now, this actually uses statistics to use this statement here. So we're going to do this later on in chapter 12 in our text. At the very end of class, we'll see how we can actually make these statements. But there's actually a lot of math and checking behind this. So when we make a statement like this using statistics, we actually have to make sure we have a large enough sample size, that it was sampled correctly, so that our sample of people comes from all different areas that represents the population. And then we do a lot of calculations to actually get these numbers. So notice that we have a 95% probability that it's between these two values. It's not a 100% true statement, but we feel very confident, like 95% confident, that our statement is true. And again, this is using statistics. So there's actually a lot of math going on behind here that we're going to see later on in our course. Here's an example of a weak argument. Neither my father nor my brother has ever cried in front of me. Therefore, men have difficulty expressing their feelings. So let's talk about why this is a problem. So first of all, I'm using only two people, right? My father and my brother as my example. Here, look at our example. We had 380,000 people that we looked at, right? Here I have two people. So first of all, my sample is very, very small. Secondly, the other problem is that we're using people we know. So a lot of times people draw conclusions based on their own personal experiences, and these can be great too. So our personal experiences are really important, but it doesn't mean that we should always generalize our personal experiences to everybody else, right? So just because, and again, this is not a true example, by the way. This is not my actual father or brother. But if, for example, I had never seen my father or my brother cry, I'm making a general statement about all men versus on just two examples of my own personal family, right? So that's not a good argument there. You want to make sure that when you're making these arguments, you have a large enough sample. So a sample that represents the population. So we want a sample that represents all men, right? And we want to be really careful about our own personal experiences. Again, personal experiences are wonderful, and they help us learn about life and how to succeed and how to, really work on our own challenges and what to expect as well. So those patterns there are still important. But just because it's something we have seen in our life does not mean everybody sees things that way. So another example, using a personal experience, I grew up in Lowell, Massachusetts. So it's a pretty large city. And in my high school, I had about 4,000 students. So a weak argument, for instance, could be something like, well, I went to school with 4,000 students in my high school. All students must have high schools that are very large as well, right? That's not a true statement. I think some of you probably went to very small high schools. Some of you maybe went to large high schools. But me taking my own one personal experience of my own high school and trying to extend that to everybody just doesn't work. So we just want to be careful with what we're looking at for our samples there. Now, another thing that we can use inductive reasoning for is to figure out patterns. So here we just have some kind of fun number patterns that we can do to see if we can figure out that next number in the group. And some are easy and some are hard. These are ones, if you want to get some extra paper out, you can. So if you just kind of want to spread out and see what's going on a little bit, I think I actually will do that myself. Just grab an extra paper. All right, so let's do these examples together. So the first example, I see the numbers 3, 12, 21, 30, 39. Yeah, I'll just write a couple of them out. Okay, so there's our first couple of examples here. And then basically what you want to do is you just kind of want to look through and see if you can figure out the pattern. Some of these are easy, some of these are difficult. So again, I'm going to work on A first. And they could take a little bit of trial and error, just kind of figure it out. So do I see any patterns? Things that you can try when you're looking for patterns are addition or subtraction patterns, multiplication or division patterns. So those are our simplest patterns. So here, if I'm looking, I may first by saying, okay, well, what's the change? So from 3 to 12, this is a +9 change, or I may say, hey, that's a ×4 change, right? So you're kind of looking to see is there a pattern here. If I go from 12 to 21, now 12 times 4 is 48, so that doesn't look right. That's not going to work here. But 12 to 21 is +9. And then 21 to 30 is also +9. And 30 to 39 is also +9. So it looks like I found the pattern here. Again, addition and multiplication, or addition, subtraction, multiplying, dividing, tend to be our most common patterns, although there could be others. So I usually say start with that. See if you can add or multiply or subtract or divide to get to the next number. So this +9 is working. So to find that next value, I'm going to take my 39 and I'm going to add 9 to it again. And that should give me the next value in my list. All right, so let's do the next one now. So here I have 3, 12, 18, 192, 768. Again, let's see if I can find a pattern here. So if I start with adding, I know 3 to 12 is +9. And then 12 to 18, let's see, is +6. And then this is a really big jump, right? So this doesn't seem to be working, right? It doesn't seem to work for me. All right, so it's got to be something else. Oh, let's see. And actually, I found a little mistake here. No wonder it's not working. I missed the number when I was typing. So this one right here, I apologize, should be 48, and that makes much more sense. Just trying to make any other typos. There we go. So let's see, this is 48. Again, I'm going to +9, and then I'm going to a much larger number. So again, that adding pattern doesn't seem to be working here. But let's try multiplying. This is ×4. So 3 times 4 is 12. 12 times 4 is 48. If I check 48 times 4, let's see, I get 32, and then I get 16 plus 3 is 19, so I get 192, so that seems to check. If I check this times 4, get 8, see, 36, and then 7, so I do get 768, so that ×4 pattern seems to be the one that's working here. Again, I apologize about that typo there, so that makes much more sense now. And make sure you guys check too. So I do the same mistakes as you guys sometimes. So when I'm writing a problem down, here I was typing it, I typed one digit wrong and then the whole thing becomes off. So if you're getting stuck, just make sure you wrote the problem down right. Just like I did here, double check my problem in the text to make sure I had it right. So this ×4 pattern seems to work. So I'm going to take that 768 and I'm going to multiply it by 4. Now, you can use calculators in this class, so I'm going to cheat and go ahead and get my answer as well. And we should get 3,072. So there are the first two patterns. Now, again, this is a good time in the video if you want to pause it and try the next two on your own. See if you can figure out that pattern first. That would be a great idea. Let's keep going. Again, I'm just going to double check now. Now I feel like I must have typed something else wrong. Let's make sure. Now the next one looks good. So let's see if we can find our pattern here. So I have 3, I have 4, 6, and 9, 13, and 18. All right, so again, I usually like to start with adding and multiplying to see if there's anything there first. So here I see +1. Here I see +2. So not the same, but +1, +2. Next I see +3. So I am seeing some sort of pattern. It's not as obvious when I first look at the numbers, but I can see that I'm actually adding one more value each time, right? Here's +1, 2, 3, 4, 5. So my next value must be +6. So I take my 18 and I'm going to go ahead and add 6 to it. So for my next answer, I should be looking at 24. And then let's check the last one. So 3, 6, 18, 36, 108, 216. That looks good. Okay. So again, let's see if we can find a pattern here. So here I see +3. And let's see, I see +12. And then I see +18. I don't know, am I seeing a real pattern here? I don't know, let's try something else. 3 to 6 is times 2. 6 to 18 is times 3. 18 to 36, that's times 2. 36 to 108, so let's see, 36 times 3 is 108. 108 to 216 is times 2. So actually, this is a tough pattern as well. It is a multiplication pattern, but we're switching between multiplying from 2 and 3 back and forth. So in the first case, we multiplied by 2, then by 3, by 2, by 3, by 2. And that means the next one then is going to be times 3. So if I do 216 times 3, again, I'm going to cheat here and come down and use my answer. My calculator is 648. And I see my final answer there. So here we're using inductive reasoning as well, obviously in a different way, right? So looking at patterns with numbers, but we can use that too. So we look at what we already know, find the patterns we see, and then we predict what the next number would potentially be. When you're doing these, some of these can get really tricky. So I suggest starting with adding and multiplying. It's not always the case, but a lot of times we do have a lot of adding and multiplication patterns. Similarly, you could see subtraction or division patterns. So I tend to start there first. So I kind of look to see, okay, what am I adding between each value? What am I multiplying between each value? Check for a pattern there first. Usually that will help you. All right, so let's do a couple more examples with patterns. And then we'll look at deductive reasoning. So again, here's a good time where pause the video, give it a try first, see if you can figure it out. These are a little bit tougher, but we can still do them. So for this one here, if you notice the pattern, it's a little hard to see, but we have 1 to 1 to 2 to 3 to 5 to 8 to 13 to 21. So if you're thinking about an adding pattern first, you may think, okay, this is +0, +1, that's +1, that's +2, that's +3. This is getting kind of weird, right? I don't really see a clear adding pattern. 0, 1, 1, 2, 3. So it doesn't really work that well. If I try multiplying, again, it's I don't really see anything clearly. So the pattern here, this is actually a really special pattern. It is an adding pattern, but it's a little hard to see. So this is actually called the Fibonacci sequence. And it's a special pattern where you add the 2 digits before. So notice that 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. So to get the next number, I add 2 values before it. So 21 plus 13 is going to give me that 34. And again, this is a little tougher to see here. So this is actually called the Fibonacci sequence. So it's a really special pattern where we're adding the 2 digits before, or the 2 values, I should say before, not necessarily digits. So the 2 values before. This is another one, again, that's challenging. So example 3 is pretty tough, I think. They're not your standard, just basic adding or multiplying examples. We do have addition here, but it's a little bit more complicated. Here, again, this one is pretty complicated. We do see some addition going on, but not in the way that you're maybe expecting it. So it's a little similar to the idea of the Fibonacci sequence where you're kind of adding things together. So what I want you to notice is there's 2 patterns actually going on here. So the first is with the first digit. So notice here, if I did 2 plus 3, I get 5. And then notice if I do 5 plus 4, I get 9. And then if I do 9 plus 5, I get 14. Let's see, let me get a different color now. Now add up the other digits. I have a 1 plus a 4 plus a 6, right? 1 plus 4 plus 6, that's 11. So there's the 11. And then here, 1 plus 1 plus 7, that gives me the 9. So the first digit of the next number comes from adding the digits before. So here, if I add a 9 and an 8, I'm going to get 17. So 17 is going to be my first set of values, or my first digits. Now, what's the pattern for the next number? Again, these are not that easy. This one's pretty tricky. So let's see what's going on here. I'm going from 3 to 4, 5, 6, 7 to 8. So see that second digit? It's 3, then 4, 5, 6, 7, 8. So if I look at that, my next value would be 9. So my answer then is 170. Okay, so it's just some examples of simple patterns versus much more difficult patterns that we can find with numbers. So they do get hard and they do take a little bit of trial and error as you're going through. Now, one thing to note is it is possible as well that an initial list of numbers could have more than one pattern. So, when we're doing these conjectures, again, we're not necessarily stating truth. So sometimes there could be other patterns, and maybe one sequence of numbers could have 2 different patterns. And we would need more examples before we can feel more strongly about our answer, right? So for instance, let's consider the numbers 1, 2, and 4. So let's say I gave you the example 1, 2, 4, and then I said, what's the next value? Well, there's different people that could read it different ways. So for instance, one way to think about it is we could get the next number is 8. Because we're saying, okay, well, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 must be 8, right? So that would be the next number. But that's not the only pattern that's there. There's actually a different pattern that someone else may see. So here's the second pattern. And it's called successive counting, meaning that we're adding 1 each time we count. So successive counting means to add 1 more each time you're counting. So for instance, let me rewrite this. 1, 4. So here we're adding 1. Then here we've added 2. So if we're following this pattern, then next we should add 3. So this is called successive counting. So you're adding 1 each time. So then 4 plus 3 would be 7. Okay, so again, if you have more examples, so here we have a lot more numbers than just 3. It's a little bit easier to get a specific answer, right? Because you have more examples that are leading you to a stronger conclusion that this is the pattern. Here I only have 3 examples, so it's not as strong. It's a little bit weaker where I see one pattern here and a second pattern here. So I'm not maybe feeling as confident about my final answer. So sometimes we could have multiple patterns, but like I said, the more data you have, then the easier it is to narrow down what that pattern is. So that way we can get stronger inductive conclusions rather than weaker inductive conclusions, right? Now, it's not just about numbers. We have a lot of visual patterns too, especially in nature as well. So if you think about patterns, look at a butterfly, right? You have 2 sides of the wings that are usually symmetric, so they're the same. So we have patterns everywhere. Here's just one example. So let's say we want to find out what the next figure should be in the sequence. So first thing I notice is I see circle, square, circle, square. So my brain is telling me that, okay, there's probably going to be a circle left next. And all my values seem to be cut kind of like in these quadrants. So I'm just going to start with that shape. Now I know there's dots in here, so I got to figure out how the dots go. So think about what's going on. I'm going to look a little bit deeper now. So notice that with my circle, I started with the dot here on the right, and then it looked like this circle rotated. It kind of twisted around, and my dot is here on the left. So I went 1, 2, 3 dots, and then 1, 2, 3 dots. The same thing happened here. For my square, my dot was here, and it looks like it rotated, right? So it's rotating down to here. So notice that leading single dot. So I have always a 1, 2, 3 dot pattern. 1, 2, 3. Right? So notice that it's rotating around, right? It starts on the right, then it goes up top, then it goes to the left, then it goes down bottom. So I see that the single dot is kind of rotating around, and then following it would be the 2 and the 3 dots. So I'm going to keep following this pattern. It went right, top, left, down. So if I'm down, it should be here, right? So I'm going to look back here to figure out where my other dots are going to be. So that would be my conclusion on what the next shape would be. Right? So this is inductive reasoning. Inductive reasoning takes specific examples, and then we try to apply a general concept using the specific examples to help us. So we're looking for those patterns.